Okay, I'm gonna start another video. So we just talked about like the location for constructing the moon base is everything. And in this chat GPT conversation section, I said if the nuclear reactor was underground on the moon, and it was powered on, it the nuclear reactor is underground, so you have lots of natural protection from things, and it is powered on. The nuclear reactor, by being powered on, it will be producing its own radiation slash ion radiation just for the nuclear reactor powering on. And that is correct. Chat GPT confirms that the nuclear reactor being turned on will itself produces ion radiation. And I made the assumption that the ion radiation being produced, it would eventually fill the underground and make the underground very lots of radiation in the underground, and that could be bad. But however, apparently nuclear reactors, from the inside of the nuclear reactor has a lot of shielding to prevent radiation from leaking into the outside environment. So like this shielding could be very thick concrete. I guess it's called radiation shielding. I mean, shielding of ionizing radiation for power plants and nuclear reactors. Um, Hold on. Let me find something really quick. It does emit ionizing radiation, but nuclear reactors are designed with shielding to keep that radiation, the ionizing radiation, from escaping into occupied areas. And the shielding that is on the inside of the nuclear reactor, the shielding may include the reactor vessel and dense materials such as steel and concrete, like earth, like concrete on earth. So this shielding right here, it will prevent radiation from leaking into other environments. And then also, by having the nuclear reactor on the moon, I guess that there could be a way to um, surround the nuclear reactor with regolith. So like, there's like a nuclear reactor, right? Nuclear reactor. Okay, so like let's just say, well, it's a lot bigger than I imagined. But like let's just say you could just like surround this thing with regolith, in which the ion radiation will travel outwards and hit the regolith, and it cannot penetrate past the regolith. So, kind of using regolith as a shielding strategy to prevent ionizing radiation from leaking into the environment. But hold on. Let's see if that thing is actually possible. Nuclear reactor using moon regolith to prevent ionizing radiation from leaking into the outside environment. Okay. But anyways, there was no AI response. But anyways, hopefully you understood what I was talking about of the concept of the nuclear reactor existing underground, which is protected against micrometeorite impacts and moon's natural harmful radiation that exists naturally and charged particles. But when the nuclear reactor is turned on, the nuclear reactor is going to naturally self-produce ionizing radiation. And I guess even though the humans are in astronaut suits, and the astronaut suits are designed to limit radiation exposure, but I guess if you want the nuclear reactor to not leak ionizing radiation into the outside environment, all you have to do is use regolith as a shield. Regolith surrounds this thing. And the ionizing radiation is going to travel outwards like this, hit the regolith, and basically it cannot get past the regolith to travel to the outside environment. Okay. Okay, so in order to power the moon data center, remember the moon data center, to power the moon data center for humans to live in / astronauts to live in, it needs electricity to power, or energy sources to power, to operate. Plus, that electricity will eventually turn into waste heat, in which it needs to be radiated into outer space via radiators. And basically, I said that there should be a hybrid system to power the moon astronaut base. And I am not including the data center. I'm just talking about powering the moon astronaut base. And there's a hybrid system of solar panels and battery storages and nuclear reactors underground. And so, after inputting that information into ChatGPT and other things like that, like this system, ChatGPT said something like, but basically after reading what ChatGPT had said, basically the main source of power is going to be nuclear energy. That is the main source of power because it is the most reliable, the most consistent, the most constant, and humans have complete control over the nuclear reactor producing 5 megawatts of electricity 24/7 forever. Whereas for these things, it's just, there's a lot more things that can go wrong and you have to consider. And this exists underground, so that presents enormous advantages. This exists on the surface, however, you do have to worry about micrometeorite impacts and moon's harmful radiation and charged particles, so this might need to be maintained on a more regular basis. This, perhaps can exist underground, but who knows, it's used for emergency purposes. This would be the main source of energy all the time. Solar panels could be used when it's daytime. So, solar panels are used in daytime, and then it gives, humans can tell the nuclear reactor to be producing 24/7 less than 5 megawatts of electricity, or it could be like 2 megawatts of electricity. And the solar panels could activate since it's daytime, puts less stress on the nuclear reactor. So main source only used during certain periods, like mainly used during daytime. And in the backup batteries, it will store energy or store electricity to be used in emergency situations. And when those emergency situations do arise, because maybe these things are completely shut off or in maintenance, and these things have to be relied on greatly, or maybe there's some type of energy malfunction or energy spike, and these things cannot handle that energy spike right at that time. So then the backup batteries, the emergency power kicks in, and it fulfills those energy spikes. But however, remember, main one all the time, main source of energy all the time, secondary source of energy during the daytime, and this is used for emergency purposes in case of electricity spikes or something like that. But also remember, you also still need radiator farms, because radiators are the only way, or are the only mechanism to effectively radiate the heat into outer space, or expel the heat into outer space. do not really worry about this because ChatGPT said something else about it. Okay, this was the okay, so hopefully you understood the aspect about this is always the main source of energy 24/7 forever. That is the main source right there. This is the secondary source, only used primarily used in daytime, and then this is the backup for emergency situations whenever that arises. And you also still need radiators for a certain purpose and radiator farms for certain purposes to expel the heat into outer space or radiate the heat into outer space. Anyways, bury the nuclear reactor underground. Bury it deeply enough to provide the desired protection that I said. No, it did not say in here. Bury the nuclear reactor underground deep enough to pretty much 100% prevent these types of micrometeorite impacts that could be absolutely devastating to a nuclear reactor. So that is why you want to bury the nuclear reactor deep enough underground on the moon to provide the desired protection, and you can monitor its condition over time and monitor other things. And then, if it ever reaches the end of its service life, building a new one might be more practical and easier than, relocating an existing one. Okay, so basically to power a moon base that in which supports 4 through 12 astronauts, so maximum 12 astronauts, minimum 4 astronauts, and the radius of the hollow pipe is 10 meters through 20 meters. Basically so when I was creating this document, which is said in here, this link right here, I had a long discussion with ChatGPT that the document is actually hundreds of pages long. However, this is just a too long did not read section that is that long. And basically, these are just some summaries of ChatGPT. Hollow pipe design of a very small one is radius of 10 through 20 meters for the hollow pipe that humans live in. So humans live in a hollow pipe. They're attached to it. They're attached inside the hollow pipe, and the hollow pipe has a diameter of 10 meters through 20 meters. and the hollow pipe is rotating, the rotations of four rotations per minute to 6 rotations per minute, and you're rotating the hollow pipe to create artificial gravity, to create centrifugal force, to get gravity measurement to be greater than 1.6 meters per second squared. However, it's anyways, and basically using this example that ChatGPT had generated, which can be done, using this example, radius 10 through 20 meters per second squared, rotations per minute is 4 through 6. ChatGPT was saying for that example that the energy needs scaled down, so this is just an underestimation, but it is realistic. The daily usage for life support for the moon base is 100 kilowatts through to 300 kilowatts. The heating/cooling is 50 kilowatts to 150 kilowatts. The systems plus lighting is 50 kilowatts to 100 kilowatts, and the rotating module is 5 kilowatts through 20 kilowatts. So these are like the moon base features, the power it needs on a very consistent basis, and the life support for the human astronauts inside the moon base, what they need on a consistent basis. But basically the bigger picture to look at is how much electricity do you need in total on a consistent basis. And basically after adding these up and maybe scaling it up, it says you will need in total about 5 megawatt hours to 15 megawatt hours per day. Okay, and now I would say a nuclear reactor can easily sustain 5 megawatt hours to 15 megawatt hours per day. A nuclear reactor can easily sustain that aspect. However, can easily sustain this aspect right here that is highlighted. However, right here, it says that compared to 100 megawatt hours to 250 megawatt hours for larger bases. So, 5 through 15 megawatt hours can easily be sustained by a nuclear reactor or a small nuclear reactor. However, for something that is 100 megawatt hours to 250 megawatt hours, you would need a much larger nuclear reactor or multiple nuclear reactors. But also, 5 through 15, this design right here. Okay, 5 through 15, this design right here can easily be sustained and can realistically be achieved quite easily. However, so that was only for 10 meters through 20 meters in diameter. However, if the diameter was 100 meters through 200 meters in diameter, this would be for the rotating hollow pipe. Okay, so you went from 10 to 20 meters, all the way that requires 5 megawatt hours of electricity to 15 megawatt hours of electricity, and now you are going to jump all the way to a much larger diameter, 100 through 200, for the rotating hollow pipe. Plus, it also is this large number of 100 through 250 is also supporting the life support mechanisms for 200-meter diameter, the heating / cooling for a 200-meter diameter hollow pipe, and the systems plus lighting for a 200-meter diameter, and a rotating module for a 200-meter diameter. Basically, this is not sustainable. I mean, a nuclear reactor could technically produce this amount of electricity on a consistent basis, but you also need to think about, can the radiators effectively and consistently radiate into space the heat that is generated from 100 megawatts of electricity? And the realistic answer is probably the radiators cannot radiate into heat 100 megawatts of electricity. However, the radiators could radiate into outer space 15 megawatts of electricity. So that is why this is more sustainable, and that is why, something like the hollow pipe design of this is more sustainable. Hopefully, you know what I am talking about. Anyways, so sustainable. The key aspect for establishing a moon base is to hypothetically create a moon civilization, but it's mainly just for, certain purposes, and it's mainly to harvest resources on the moon's environment plus soil plus etc., so that people who are funding these space expeditions / investors giving money to companies, they can get a return on their investment, which allows for more money in the future. And also it produces a good result for Earth and a good result for humanity. But anyways, a radius of 200 meters is completely unsustainable because of how much electricity that it needs on a consistent basis, which the nuclear reactor can technically support 100 plus megawatts of electricity on a consistent basis, but however, can the radiators expel 100 megawatts of heat on a consistent basis? And that would be a big fat no. The radiators cannot expel 100 plus megawatts of electricity on a consistent basis. So you need to think about the radiators as well. But however, for this, it is more sustainable for the radiators, and for this, it is more sustainable for the radiators as well. So the radiators, you really need to think, can the radiators effectively radiate this much heat generated into outer space on a consistent basis? Because that is very important as well. Anyways, I did type this information into ChatGPT, and ChatGPT explains it a little bit better. Okay, anyways, so ChatGPT responds, okay, so the best thing is to mainly focus on the moon base for astronauts plus moon base life support systems. We are not talking about the moon data center, we are talking about the moon base and moon base life support systems. What is your / ChatGPT's opinions about the thing below? Rotating hollow pipe that the astronauts are inside, creating artificial gravity plus astronaut life support things. They need power to be in operation. So anyways, the rotating hollow pipe plus etc. houses 4 through 12 astronauts. The radius of the hollow pipe is 10 meters to 20 meters that is rotating to create a greater gravity measurement. Anyways, so these things house these many astronauts. It is this big in diameter or radius, and it is rotating, so it needs electricity as well. Are the below numbers accurate to support astronaut life supports things inside a hollow pipe that is this big, in which the life support total electricity needed is 100 kilowatts to 300 kilowatts. The heating / cooling total electricity needed is 50 kilowatts to 150 kilowatts. The systems plus lighting total electricity needed is 50 kilowatts to 100 kilowatts. The rotating module total electricity needed is 5 kilowatts to 20 kilowatts. Total electricity needed 24/7 or forever is 5 megawatt hours to 15 megawatt hours. Anyways, mainly focusing on these numbers and these numbers that are in the highlighted blue section. Are those numbers accurate to support that specific rotating hollow pipe generating artificial gravity plus astronaut life support mechanisms plus etc.? If those numbers are accurate, it seems that a nuclear reactor can easily generate that much electricity. Okay, and remember, a nuclear reactor can do that, and also most importantly that radiators, like the cheaper radiators, can somewhat easily expel / radiate 15 megawatts of electricity, the heat generated, into outer space. They can somewhat easily do this. And what is ChatGPT's response? Basically, ChatGPT says that your numbers are in the right order of magnitude, as in like it's a somewhat accurate estimation. I mean, it could be underestimated, but basically it just adds up to like 15 megawatts, and 15 megawatts is okay for radiators as well. But anyways, your numbers are in the right order of magnitude, but your numbers should be treated as rough conceptual estimates, not design values. And they are rough conceptual estimates. They are estimates because in in here it says these energy needs, which are scaled down, so they are underestimated, but they fall into the range of 15. They could be as high as 30, who knows. They should be treated as rough estimates and not absolute design values. There are many unknowns to consider, like the habitat volume, the insulation, the crew activity, the recycling systems, the artificial gravity design slash etc. But anyways, let's look at it. Let's look at each category. The system of life support, 100 kilowatts to 300 kilowatt estimation, and then ChatGPT's assessment is reasonable for a small but capable habitat on the moon with air recycling, with water processing, and other environmental systems. Hold on 1 second. Oh, so basically, it mentioned something about water processing systems. And water is going to be very valuable for having humans to be living long term on the moon, because water is essential for human life. Like water is essential. Humans cannot live that long without water, so having water is essential. And in this article right here by Yahoo, basically this was published in on May 28th of 2026, and basically they're eventually I think sometime in July of 2026, there's going to be surveillance on the moon just to find the right location to construct all of these things, and these drones and cameras are going to have be high tech to detect even underground, and they're going to detect other things as well, such as they're going to detect the cameras for lunar plume surface studies, in which these cameras are designed to record how the engine of the rocket ship Plume, when it lands down, like the rocket ship is right in the sky, and then when the rocket ship lands down onto the moon, the high-tech cameras are going to record and measure and all of these other things, how the dust and things like that, like if the dust hits the rocket ship, how much, if it will cause a lot of damage. Understanding how the engine plume, so the rocket ship lands on the moon and then there's dust hitting it, interacts with the surface on the moon in microgravity or 1.6 meters per second squared gravity environment or 0 meters per second squared gravity environment, is important to a safe landing. Okay, because as that the high-speed exhaust could interact with the moon surface, and the interaction between the high-speed exhaust and the moon surface, it could create flying debris like the moon dust that could hit and damage the spacecraft during the landing. So the cameras are going to measure stuff like that. But anyways, oh my gosh. Okay, so we were talking about water. We were talking about water processing. Okay, so I guess that was in another article. Oh, oh my gosh, dude. Was it in this one? Basically, in one of these articles, okay, but basically in one of these articles, basically it said that NASA found water on the moon, such as things like glaciers on the moon, dark side of the moon. I guess they found it many years ago. Okay, but they said they found it in this particular location. So, uh, so when I was reading the original article, it was talking about the moon's south pole region, or the dark side of the moon, because very little sunlight gets there, I guess. But basically, it's about, water, ice and water found on the moon that could be converted into. They say things that, like, oh, for rocket fuel. But I would also say that can be converted into possibly drinking water, or it has to go through some type of purification process to be drinkable water. But let's see something. Let's see what an AI response says. There's this Wikipedia link. Well, anyways, I'll ask ChatGPT later about this water thing. So life support 100 kilowatts to 300 kilowatts reasonable for etc. Doing etc. Heating slash cooling 50 kilowatts to 150 kilowatts plausible, perhaps achievable, most likely, though it depends on things. Lighting in general systems with 50 kilowatts to 100 kilowatts is reasonable for stuff in rotating habitat 5 kilowatts to 20 kilowatts reasonable. And it says gives a total continuous electrical demand of roughly 205 kilowatts to 570 kilowatts, which is much, much, much less than 15 megawatts. But these numbers is equivalent to 0.2 megawatts to 0.6 megawatts, and which basically the radiators can sustain 0.6 megawatts. And basically, regardless of all of this stuff, basically it's just the main thing is, what is the total electricity usage in terms of megawatts? Is it 1 megawatt? Is it 5 megawatts? Is it 10 megawatts? Is it 20 megawatts? If it's 20 megawatts, can the radiators effectively expel 20 megawatts of heat that was generated into outer space, or can the radiators effectively radiate 20 megawatts of heat into outer space on a consistent basis? Because the radiators are extremely important to making everything run smoothly. Anyways, so alright. If the habitat continuously uses 0.2 megawatts, then over 24 hours it consumes about 4.8 megawatt hours. Over a 24-hour period, can the radiators effectively radiate into outer space the heat that is produced by 4.8 megawatt hours per day? Now on the high end, if it was 0.6 megawatts, then over 24 hours it consumes about 13.7 megawatt hours per day per 24 hours. Can the radiators effectively radiate the heat into outer space of 13.7 megawatts or 13.7 megawatt hours? So your estimate of roughly 5 to 15 megawatt hours per day is internally consistent with those numbers. So this is achievable, and this can be closer to realistically achievable with the radiators on the moon, because the radiators radiating heat into outer space is extremely important for things to run smoothly and everything to go according to plan. But anyways, with that being said, that general summary right here and stuff like that, now we are on another thing. Could a nuclear reactor support 15 megawatt hours per day, or 15 megawatts of electricity per day on a continuous, consistent, and constant basis. Yes, a nuclear reactor producing around 0.5 megawatts to 1 megawatt of electrical power, something associated with this, and then you have to combine it over a 24-hour period, producing around this much amount of electrical power could plausibly, or closer to realistically, support a habitat in this range, with some margin for additional support. Future moon bases might eventually use larger nuclear reactors, if they include mining operations, manufacturing stuff, scientific laboratories stuff, extensive robotics stuff, or many more astronauts. However, even though the nuclear reactor can support much more electricity, remember, the key thing is, can the radiators radiate 20 megawatts of electricity heat into space? Can the radiators radiate 30 megawatts of electricity into space? Can the radiators radiate 50 megawatts of electricity into space? If the radiators can do this, then everything is good. If the radiators cannot do this, then do not even try, because the only way to expel heat into space, or the only way to remove heat from the system, is through radiators radiating heat into outer space. But technically, with 15 megawatts, it can do this. Would the radiators be manageable for 15 megawatts of electricity? For a habitat using a few hundred kilowatts of electrical power, the waste heat is much more manageable. The waste heat is much more manageable for the radiators. But for a multi-gigawatt AI data center, the waste heat is definitely not manageable for radiators. So the electricity measurements is from kilowatts to megawatts to gigawatts to terawatts. It's kind of like kilobytes to megabytes to gigabytes to terabytes. Kilobytes lowest tiered, megabytes above that. But anything related to a gigawatt on the moon is going to be absolutely not even possible. I mean, the nuclear reactor can support gigawatts, but the radiators definitely cannot and absolutely not support gigawatts. I mean, unless there is like significant technological advancement, in the future, like 30 years from now, because the radiators would have to be that well designed. And then remember, the radiators also have to exist on Moon's surface, so that is directly in the presence of micrometeorite impacts and moon radiation and charged particles. So this can be sustained by radiators, maybe kilowatts and megawatts, but gigawatts absolutely not. But would the radiators be manageable to megawatts? Possibly. That is one of the reasons your idea of focusing first on moon habitat, moon bases for humans is practical. Hundreds of kilowatts to around a megawatt of heat rejection is challenging, but it is far, far, far smaller than rejecting the waste of heat from a 1 gigawatt data center. Bad number, bad measurement, good measurement. The radiator system is correspondingly much smaller and easier to engineer when you are thinking in terms of kilowatts and megawatts. So by megawatts, it would be like less than 50 megawatts, probably. The radiator system is much smaller and the radiator system is easier to engineer on the moon. One point about the rotating module. The rotation itself is not usually the largest power consumer. Most of the energy for rotating the hollow pipe goes into initially spinning the rotating hollow pipe up, and then occasional speed corrections after that if it starts slowing down, and overcoming bearing loss if applicable, attitude control. If the rotating hollow pipe is well designed, it can continue spinning. So like once it initially starts spinning, and you also have the spinning structure in a low gravity measurement environment, and mainly because it is in a low gravity measurement environment and there is no atmosphere and no wind, after it initially starts spinning, the spinning becomes relatively easy to do with little power afterwards because of low gravity measurement environment and no wind. So the rotating hollow pipe can greatly maintain angular momentum in low gravity measurement environments and no wind environments as well. No atmosphere environments. Angular momentum. Overall assessment. Your progression now seems much more realistic than if you were to start with a large moon data center. A possible long-term sequence would be robotic exploration, surveilling, moon base to support a small amount of astronauts, 10 meters through 20 meters, 5 megawatts of electricity through 15 megawatts of electricity, reliable power, likely included via nuclear reactors, and then you also have the solar powers and backup batteries, resource extraction and infrastructure, expanded scientific facilities, and then larger computing facilities if there is a demonstrated need for local high performance computing. Radiators are extremely important. That sequence builds the supporting infrastructure first, making later projects such as dedicated moon data centers much more possible in the future. Okay, anyways, now let's ask ChatGPT this question. So this is about the water that apparently was found on the moon. And ChatGPT says, like, yes, in principle, water ice on the moon can be converted into drinking water for astronauts, which is important. In fact, this is one of the main reasons space agencies are interested in the moon's polar regions, like the South Pole region of the moon or the North Pole region of the moon. And also it can, having reliable drinking water can make it so that humans can stay on the moon for longer periods of time. The moon does not have glaciers like Earth. The moon does not have glaciers. Instead, scientists have found strong evidence for water ice on the moon, that the water ice is permanently shadowed. The water ice in permanently shadowed craters near the lunar poles on the moon. So this would basically be water ice inside of craters, but the craters are rarely ever exposed to sunlight, because if they were exposed to sunlight, I'm pretty sure they would start melting. Moon craters are rarely ever exposed to sunlight. So, this is, another instance of the phrase, the dark side of the moon. And, who knows how deep these craters actually are. It's just that these craters, sunlight is rarely ever, or is never exposed to these craters. And so I'm pretty sure that is why, one of the reasons why, moon ice has formed. What is it called? Water ice. Water ice forms on the moon inside moon craters because the craters are rarely ever exposed to sunlight. Okay, you can read that Wikipedia thing, and you can read all of this stuff on the page if you want to. Okay, anyways, these craters that rarely ever see sunlight are so cold that ice can remain stable for billions of years. Oh my gosh, that's amazing. How could moon water ice become drinking water? The basic process of converting moon water ice into human drinking water would be to mine the icy regolith, the moon's soil mixed with ice. Hopefully you know what regolith is. And then heat the material over a fire so the ice turns into water vapor. Capture and condense the vapor into liquid water. Filter and purify it, the water, to remove the dust, salts, and other contaminants, and test the water to ensure it meets drinking standards. So it's like Earth filtration of water, but applying it on the moon. This is similar in principle to how water is purified on the International Space Station. So it is already done on the International Space Station, that it is existing in open space / cold space / free space, although the source material is different, because the source material is going to be moon ice water. Could astronauts drink it? Yes, but only after purification. Now you have to get all these impurities out, and so they have to design some type of purification water filtration system for moon water ice, or ice regolith. Why is moon water so valuable? Water is one of the most important resources for a permanent moon base, because water, if it is turned into human drinking water and things like that, can support multiple needs. Drinking water for astronauts, food preparation. Although if the water were to have these minerals still left in it, I wonder if it could be for food preparation for moon purposes. Water is used for hygiene. Water is used for oxygen production by doing this sciencey stuff. Water can be used for rocket propellant by doing this sciencey stuff. This means astronauts would not have to launch all of their water from Earth, which could greatly reduce the cost of long-term moon operations. Is this confirmed? Yes. Multiple missions, including NASA's LCROSS mission, impact experiment, and observations from missions, such as Lunar Renaissance Orbiter, have provided strong evidence that significant water-moon ice exists in permanently shattered regions near the moon's pole areas. However, the purification has not actually been done. But anyways, this is one of the major reasons the moon south polar region has become a primary target for future human exploration. Okay, so that question was mainly about, can this moon ice water be converted into human drinking water for humans, because that is important. Okay, now let's ask another question. Can radiators on the moon effectively radiate into space heat that was generated by 15 megawatts of electricity location is on the moon. Okay, now, in this one I said 15 megawatts of electricity for if radiators can handle that. I mean, I could say 20 megawatts of electricity or 50 megawatts of electricity, but who knows? That's just like something to test out. And remember, the radiators have to be exposed to moon's surface. They have to be exposed to outer space, and radiators also are most likely going to have to undergo regular maintenance because of moon's surface always being impacted by micrometeorites and um, moon's surface. They're exposed to moon's natural harmful radiation and from charged particles, and these things, by hitting the radiators, can cause electronic malfunctions for the radiator electronic pieces, unless the radiator is hardened. Radiation hardened radiators. That helps delay things. But anyways, can radiators radiate heat into outer space if the thing is 15 megawatts of electricity? Yes, a radiator system on the moon could be designed to reject the waste heat associated with a habitat using around 15 megawatts of electrical power. The challenge is not whether it is physically possible, because it is physically possible. The challenge is how large and sophisticated the radiator system must be. Here's why. First, 15 megawatts is a lot of power. If your lunar base continuously consumes 15 megawatts of electricity, then nearly all of that electrical energy eventually becomes waste heat that needs to be radiated into outer space. That means the cooling system must reject on the order of 15 megawatts of heat, plus additional heat from the power source itself, especially if it is a nuclear reactor. Yes, it can. Yeah, and so it's basically with the 15 megawatt measurement, it's saying that the radiator farm size needs to be about 0.01 kilometers squared or maximum 0.03 kilometers squared. So like I remember in a video that I previously made, or maybe it was in a Google document, it said something about like so much electricity was in use. I'm not sure how much it was. Like the maximum was probably like 50 megawatts of electricity. And that correlated to like the radiator farm size. Needs to be the radiator farm size plus like the total surface area of the radiators combined needed to be about it said anywhere from like 1 kilometers squared to 2 kilometers squared. Okay, so with something like 50 megawatts of electricity, the radiator total surface area size needs to be 1 kilometer squared to 2 kilometers squared. Okay, so 1 kilometer is much greater, 0.01 kilometers squared is much less. 2 kilometers squared is much greater, 0.03 kilometers squared is less. So it's already a big number difference. However, I did not know how to visualize how much 1 kilometers squared is or 2 kilometers squared. But basically, remember we're focusing on these numbers right here. But basically ChatGPT was able to say something like, to visualize it, ChatGPT said something like 2 kilometers squared is basically the size of New York Square Garden. New York Square or it was some structure in New York, like a very, very large structure. I'm not sure if it was New York Square Garden or some type of garden, but it was a very, very large structure that, apparently is massive. But that is for 2 kilometers, but that would be for the size of 2 kilometers squared. But 15 megawatts, oh, it's much less than 2 kilometers squared. So, that is more achievable to realistically build. If we're talking about traditional radiators, now advanced radiators, you'd probably need less total surface area. Liquid droplet radiators, if those are implemented, you'd need less total surface area. But anyways, the exact size depends on the radiator technology. The exact size depends on 1, the radiator technology, and 2, the operating temperature of the radiator. So these are illustrative things rather than pure fixed numbers. Is this easier than is 15 megawatts easier than 1 gigawatt for radiators to expel heat? Yes, it is. For supporting this and 10 meters to 20 meters of radius size for the rotating hollow pipe and things like that, 15 megawatts is actually a fairly generous power budget. A well-designed radiator farm could reject that heat of 15 megawatts continuously, and that would be a very good thing. And that would mean that moon bases for humans is actually realistically possible, because radiators can realistically and continuously expel this heat no problem, and that would mean that humans can live up there for longer periods of time, and that would mean that the main thing, that harvesting resources on the moon planet is actually possible, which would give returns on investments for good purposes and for future funding purposes, and also means that harvesting resources on the moon planet also means that it correlates to producing a good result for Earth and humanity. You know, such as, like, I don't know, Earth resources are left alone. Instead, people harvest resources on other planets. And so that means that since Earth resources are left alone, it means that Earth experiences a decline in climate change. Earth experiences a decline in global warming levels, and Earth experiences re-strengthening Earth's magnetic fields, which is a very good thing, by the way. So, you know, that's what that could lead to, of harvesting resources on the moon planet, like helium. Because, you know, helium is very critical for, I would say, very critical for Earth's magnetic fields. Basically, it's just that when helium reaches its critical temperature levels, it will expel, because it has reached its critical temperature levels, it will expel it will expel it once helium reaches its critical temperature levels, because it has reached its critical temperature level, it will enter into its superconducting state and start expelling magnetic fields, and the expulsion of magnetic fields plays a role in Earth's magnetic fields. Build a moon base first with power, life support, and thermal management, and consider the moon data center later if needed. Primarily not, because the moon base for humans to live in is for a couple of reasons only. And then there's this sentence right here. And I think I am done.